Hi everyone, I'm Chuan-Hua Chen. I'm the Senior Architecture Division Director of NDIS Technology. Today I'm going to briefly introduce NDIS extended RISC-V features. NDIS Technology is a Taiwan-based CPU IP company with over 2 billion NDIS embedded SoC shipped in different diverse applications. And we want to take RISC-V and to produce high-quality RISC-V cores to those markets with solutions we developed in the past 12 years. We are also a major contributor to RISC-V tools such as GCC BinUtils, NewLib, and recently LLVM and LLD. The extended features we added to RISC-V include two different parts. The first part is NDIS V5M architecture features, and the second part is the instruction. And in the architecture features, we extended two features in the platform level interrupt controller. And we also add a hardware stack safe feature. We add a feature to redirect exception to debuggers. And in the instruction extension part, our V5M instruction set architecture includes the baseline, RISC-V baseline RVIMC base integer instruction, and also includes an optional RVA instruction extension. We also added NDIS performance extension, and the optional NDIS DSP extension, and also an NDIS custom extension to add new instructions. And now I'm going to go into some details about these features. And the first is we extended the PLIC with a priority-based preemption. And in the current RISC-V privilege architecture spec, the base PLIC can select an interrupt based on priority, but cannot automatically prevent a lower priority one from interrupting a higher priority interrupt service routine. You can manage them by using software if you want to do that, but the hardware cannot do that. So NDIS extended with priority-based preemption hardware so that only higher priority ones can preempt the currently executed ISR. And another feature we extended to make the PLIC vectorized. Actually, the current V1.10 privilege architecture has already defined a vector interrupt on the local interrupts. And then why do we want to vector the PLIC? So the reason is that actually some design practice calls for a larger number of interrupts than currently the number of local interrupts. Currently the local number is based on the X length is the third. If you use 32-bit and you only have 16 local interrupts. If it's 64-bit architecture, then you only have 48 local interrupts. It's not easy to scale the local interrupts, and it makes the programming difficult. But on the other hand, it's very easy to extend the number of interrupt sources in PLIC. Okay, so we think vectorizing PLIC is more scalable and systematic. It's a better solution. And also it works on multi-core as well. And the scheme of our vectored PLIC and is introduced briefly here. The vector table entry 0 actually includes the exceptions and local interrupts except the external interrupt. The external interrupt actually is connected to the PLIC. And the vector table entry 1 and above will be used by the external interrupts from PLIC. And with this extension, the PLIC interrupt ID has to be transmitted directly from PLIC to a target. We also changed the vector table scheme a little bit. Instead of storing a jump instruction with a limited immediate range to an instruction address, we want to increase the address range for that to reach an ISR. We don't want software programmers to deal with complicated linker script to make sure the jump instruction can reach an ISR. Sometimes in the system, the memory are put in different parts of the address space. Some of them are far apart. So we want to extend that range. And another question is now if we want to go to RV64 systems, then the table size will be doubled to reduce that range. So we decided to keep that as the RV32 system. and we just store the lower 32-bit address and use the upper 32-bit address from the MTVAL CSR. So you still can reach a 4 GB address range. With those two extended PLIC features, we compare with the base PLIC, and we actually saves more than 30 instructions for dispatch and the software, the preemption overhead. And it's equivalent more than 50% instructions before entering the actual ISR. And some designs require the latency from CPU taking the interrupt to entering the ISR to be as short as possible. And we want to make that happen. And also another benefit is the ease of use for priority-based preemption. And programmer can just initialize the priorities for each interrupt in PLIC, and then software never needs to deal with it again. And we also add a stack safe feature that will use hardware to do stack overflow and underflow protection. Basically, the hardware mechanism will monitor the SP register for protection. And another use is for recording. In the protection mode, process stack is overflowed or underflowed, the hardware will generate an exception. And in the recording mode, actually, a lot of customers need that because when the system runs, you really don't know how big your stack is. With that mechanism, you can record the maximum stack usage for your applications. And in the instruction part, we add our performance extension instructions. A big part of the program is memory access. We want to reduce the instructions to do that. So we add a GP implied load store instructions to increase the immediate range so that you can use fewer instructions to access memory. And we also calculate affected address based on data type. We also add a compare and branch instruction, compare operand with a small constant. We also add some few handy instructions for zero and sign extension. And to further reduce code size, we also add a code dense extension and to use some space in the still reserve the 16-bit encoding space to try to reduce the code size further. And we also add an DSP ISR extension. The important features of this ISR extension is actually it's greater than 150 instructions. But these instructions use only GPRs. They are not using floating point registers. And it includes saturation and rounding, and it supports various few fixed point and integer data types. And it has SIMD instructions for 16-bit and 8-bit data types. And it supports many different signed and unsigned operations. And another important part of our DSP ISR extension is to include a 64-bit signed and unsigned addition and subtraction, and also 64-bit multiplication and add. And we also add a zero overhead loop. And to facilitate using the DSP ISR extension, and we add intrinsic functions so that programmers can use intrinsic functions and use that in C. And also we add features in compiler so that compiler can auto-generate the SIMD instruction based on data types or the vector data types. To benchmark the DSP ISR performance, we use two benchmarks. The first is Helic's MP3 decoder, and we first compare just with baseline ISR, and then we compare it with DSP ISR without hand optimization. And then we can immediately get a 50% cycle reduction from 22 MCPS down to 11 MCPS. It's million cycles per second. And for G.729 codec, for the encoder and decoder, you compare with the compiled codec with an optimized, including compiler and hand optimized. Hand optimization will get a 5 times speed out of 5x, and it's equivalent cycle reduction of 80%. And an important part about this feature is NDIS custom extension to allow customer to add new instructions. And for different applications, it really needs different instructions to make it as efficient as possible. So we need to add new instructions to increase performance and reduce energy. And the important part is our framework. The framework facilitates instruction design and implementation through some ACE script and some C statement and Verilog statement. And also we allow our customers to add new custom registers, memories, and port as operands. And we also, the framework will generate extended two-chain simulator RTL and verification and tests automatically. This framework will help designers to focus on the most important part of the new instruction design. And the framework will just take care of most of the tedious things for the designers. Thank you very much.